In this experiment, we will be synthesizing aspirin. With this lab, we're going to continue our focus on building a laboratory safety mindset. We will be working with more concentrating chemicals this week, so it's important that you pay close attention to your TA when they go over laboratory safety procedures. The goal of this lab is to synthesize aspirin and to be able to show using data collected in the lab that we were successful in this process. We are also going to focus on stoichiometry and the concepts of limiting reagents, theoretical yield, and percent yield. We will also talk about new experimental techniques and some other terminology used by chemists to describe chemical structures. A full list of objectives for the lab are available on the course Canvas site. Aspirin is part of a class of compounds known as NSAIDs, non-steroid anti-inflammatory drugs. Aspirin, along with other NSAIDs, are frequently used to relieve pain, fever, and inflammation. The synthesis of aspirin is relatively straightforward. The reaction of acetic anhydride and salicylic acid will produce aspirin and acetic acid as a byproduct. For this course, we're not going to focus too much on what's going on with the chemical reaction, other than to note that changes in the functional groups, specific groups of atoms like COOH here, or this OH, and how they're bonding together is changing. We are, however, going to focus our attention on the stoichiometry of the reaction and explore concepts of theoretical yield, limiting reagent, and percent yield. One of the concepts that we will be talking about in this experiment is that of limiting reagents. Whenever we have two reactants, we need to look at and see which one limits the amount of product that will be formed. This will also help us to determine the limiting reagent. Whenever you're looking at limiting reagents and trying to figure them out, try to think about making a sandwich. If you have 6 pieces of bread and 3 slices of turkey, you can make exactly 3 sandwiches using 2 slices of bread each and 1 slice of turkey. However, if you had 20 slices of bread and only 3 slices of turkey, turkey would be your limiting reagent because you cannot make more sandwiches once all of the turkey is used up. So the turkey then is your limiting reagent and the bread is your excess reagent. When we're looking at chemical reactions, we have to do some calculations to determine what the limiting reagent is. You did the same thing with the sandwich analogy, only you did that math in your head. The first thing we need to do is convert from our starting unit, whether that's grams or milliliters, to moles. Once you're in moles, you can switch between different substances or reagents using the balanced chemical equation. So you'll always want to make sure that that chemical reaction is balanced before you begin. You can then compare between different reagents to see how much of the product you were able to produce, because whichever starting material produces the least amount of product will tell you which is your limiting reagent. Remember, the limiting reagent is the reactant which produces the least amount of product. Let's look at an example. If 100 grams of aluminum and 200 grams of iron oxide, according to the reaction shown below, react together, how much aluminum oxide will be formed? So we see that we have our reaction written out. Al plus Fe2O3 yields Al2O3 plus Fe. And a note that says that it's unbalanced. So the first thing we're going to do is check and make sure that this reaction is balanced. Well, we see that on the left side, we have 1 aluminum, and on the right side, we have 2. So we're going to need to put a 2 in front of the aluminum on the left, so that now that that's balanced. Okay. If we look at our iron, we see on the left side, there are 2 irons, and on the right side, only 1. So we're going to need to put a 2 in front of the iron on the left. And then let's check really fast our oxygens. We have 3 oxygens on the left side and 3 oxygens on the right side. So now we have a balanced equation. So let me summarize what we had on the previous slide real fast. We have the balanced chemical reaction of aluminum reacting with iron oxide to form aluminum oxide and iron. And we're given 100 grams of aluminum and 200 grams of iron oxide. I've gone ahead and calculated the molar masses, and those are shown below. You can calculate the molar masses using the values found on your periodic table to verify my values. So the first thing we need to do is look at one of our reactants. So let's start with the aluminum. If we start with 100 grams of aluminum, we know that we're going to convert to moles. So since grams is on top, we're going to want grams on the bottom. So we're going to write in 26.98 grams of aluminum for 1 mole. If we look at our balanced chemical reaction, we see that for every 2 moles of aluminum, we form 1 mole of aluminum oxide. Then we can convert back to grams using the molar mass. So since moles is on top, we're going to put moles on the bottom, moles of aluminum oxide for every 101.96 grams of aluminum oxide. I'm going to check real fast that all of my units cancel out. So we started off with grams of aluminum on top. That's going to cancel with grams of aluminum on bottom. Moles of aluminum cancels with moles of aluminum. Moles of aluminum oxide cancel with moles of aluminum oxide, leaving us with grams of aluminum oxide. And if we work out the calculation, we get 189 grams of aluminum oxide. Well, that tells us what we'll produce if aluminum was the limiting reagent, but at this point, we still don't know whether it's aluminum or iron oxide, so we need to do a similar calculation with the iron oxide. So we started off with 200 grams of iron oxide, and again, we want grams to cancel out, so we're going to use the molar mass, 159.7 grams of iron oxide in 1 mole. We want moles to cancel out, so we're going to look at our balanced chemical reaction. We see that we have 1 mole of iron oxide for every 1 mole of aluminum oxide. And then again, we want to convert to grams, so we put moles on bottom again and grams on top. Again, we want to check really fast that all of our units cancel out. So we have grams to grams, moles to moles. Moles of aluminum oxide leaves us with grams. And if we work all of this out again, we get 128 grams of aluminum oxide. Therefore, the iron oxide, since it produced the smallest number of grams of aluminum oxide, the iron oxide limits the reaction and is therefore the limiting reagent. One thing you need to notice is we're starting with more iron oxide, but it ended up as our limiting reagent. We can't just look at the moles or the mass of a substance to determine whether or not it's the limiting reagent. You need to look at how much product you can produce. The maximum amount of product that you can produce from this reaction is 128 grams of aluminum oxide. Now we're going to talk a little bit about yield. In the previous example, we said the maximum amount of aluminum oxide we can produce was 128 grams, and that would be our theoretical yield. So based on the stoichiometry, the most we can possibly make is 128 grams. This is a calculated value. Our actual value is what we really get when we go into the lab and we perform the experiment, and this is usually less than the theoretical yield. Now, for our previous example, we had 128 grams that could potentially be produced. That's our theoretical yield. That is the maximum amount of product that can be formed. When we look at an experiment performed in the lab, we also have to be concerned with the actual yield, which is the amount that is actually produced. This number is less than the theoretical yield. Depending upon how your experiment went, it may be much less than the theoretical yield. We need to remember, no matter what we do, we can never have an actual yield that is greater than our theoretical yield. If you get an actual yield that's greater than your theoretical yield, either your sample isn't dry or there's some other product in your mixture. Now, it's important to understand how this could happen, so it's a good idea to look at the procedure and see where this could have gone wrong. This is part of your error analysis in your discussion section as part of your lab report. Let's look at a quick example on how to determine our yield. Remember, our theoretical yield we calculated previously was 128 grams, but let's say we only obtained 105 grams when we did the reaction. What's our percent yield? Percent yield is defined as being the actual yield over the theoretical yield times 100. So for our example, the percent yield is our actual yield, 105 grams, divided by our theoretical yield, 128 grams, times 100. So if we work this out, our percent yield is 82.0%. That's pretty good. We formed 82% of what we could have or should have formed compared to the theoretical yield. Think of it like an exam score or when you're calculating your final grade. You could score 100 points, but you don't always do that. Your actual score divided by your theoretical score equals your grade. So in our actual yield divided by our theoretical yield gives us our percent yield. Now, one thing we need to worry about when we're synthesizing aspirin is the purity of the product. There are different ways that we can purify our product, and one we'll be using today is called recrystallization. Now, if you look at the diagram, I'm going to point out several things. On the left, we have our impure sample in a container, and we can see that it's made up of both our desired compound and some impurities. We're going to choose a solvent that will dissolve up this sample, both the impurities and our product. Particularly when it's heated, it's going to dissolve up our solid that we're interested in and those impurities. But as that solvent cools, our sample will begin to recrystallize, form a precipitate, come out of solution. What we were going to be worried about today are the soluble impurities, and so we're going to cool this sample very, very slowly. Once we've cooled it, our desired product will precipitate out, and because it's precipitating out slowly, it will become more pure. The impurities will stay in the solution because they were soluble in that solvent. Now we're going to perform a vacuum filtration to remove the pure solid from the solvent, which has the dissolved impurities in it. Make sure you check out the example of the funnel setup that your TA has shown for you and the videos on how to set up a vacuum filtration. It's important that you make sure that everything is set up correctly before you begin the vacuum filtration so you can avoid a mess and also avoid losing any of your sample. If you have any questions or need help with that, please ask your TA. To check for purity of our product, we'll be performing an iron test for purity. The addition of iron 3, in this case in the form of iron 3 nitrate, to a compound containing a phenol group. Remember when I said we talked briefly about functional groups? A phenol group is a specific functional group that contains a ring with alternating double bonds and an attached OH group. If you look back at our starting materials, does one of them contain a group like this? If this reaction occurs between a phenol and the iron 3 nitrate, you will see a violet colored complex, and your solution will be very bright purple. Hopefully, you'll see a nice clear solution, which indicates that you did remove all the phenol from the reaction mixture. However, you may see some purple, and that's okay. It just lets you know that there's still some phenol in your reaction mixture. Which one of your starting materials is that? However, you need to realize that this does not test for other impurities which could be in your sample. One thing that many students struggle with on this experiment is identifying sources of error. The best thing to do is look at the procedure. For each step in the process, figure out what mistakes could have been made, things that maybe you could have prevented, or things that you really couldn't prevent, but maybe you could minimize them from happening. You should avoid listing human errors as sources of errors, such as we spilled some of our sample, or my lab partner didn't know what he was doing, or we didn't do the calculations right. If you're not sure how to do the calculations, be sure to ask for help. All of these are preventable errors, which you will need to work on in the lab to prevent. When you go to write your discussion, you will need to include an analysis of your errors, including a list of 3 possible sources of error, whether or not they caused your yield to be higher or lower than expected, and state which one, as well as how you could prevent these errors from happening in the future. A few reminders for this experiment. Record the actual volumes used for all your liquids. And remember, you should always estimate 1 decimal place beyond the markings on the glassware. For example, if you're using the 10 milliliter graduated cylinder with marking to the 10th mark, you can actually get 2 decimal places because you can estimate the difference of the volume level between the 2 markings on the glassware. It's important that you record the actual volumes and masses that you use. The values listed in the lab manual are only approximate. You do not have to get precisely what the lab manual states. You should be generally close to it, and you should record what you actually used. Also, make sure you're using distilled water to avoid introducing additional impurities into your reaction. Record the mass of the filter paper in the watch glass so that when you weigh the filter paper in the watch glass with your sample, you can subtract those 2 values so that you know what the mass of your sample was. Make sure that you let your sample dry completely in the oven before you take the mass of it. If your sample is wet, it will be heavier than you expect and will result in a % yield greater than 100%, which we said previously was physically impossible. And also, it makes it a little bit more challenging to write up your lab report. As always, if you have questions, see your TA, go to the Learning Center, or talk to the lab supervisor. Make sure that when you're ready to clean up, your salicylic acid can go in the solid waste container, otherwise known as the garbage can. Acetic anhydride is going to go in the organic waste container in our fume hood, and anything from the purity test solution can also go in the aqueous waste container in the fume hood. Those semi-micro test tubes that are glass can go in the broken glass container when they're empty. Please double check before you pour your waste into the waste container that the funnel is open or in the up position as shown on the right and not closed as shown on the left. When multiple students pour waste into the closed lid of the funnel, it becomes not only a safety hazard for others in the lab, but also a serious safety hazard that has resulted in injury of our personnel trying to prepare your labs. A couple of final hints for you. First, come prepared, meaning read the procedure in the lab manual before you come to lab. It'll often take you 2 or 3 reads through to understand what you'll be doing. Then, write your procedure in your lab notebook. You're not permitted to have the lab manual printed out with you in lab, so having this ready is essential. You will also want to identify what measurements you will need to take so you can have space for them already indicated in your lab notebook. Also, make a timeline. This is a long lab experiment, so it is essential that you have an idea how long it will take for you to perform each step. Keeping in mind, some steps require a waiting period. This also helps you figure out steps where you can multitask. Do you have to wait for a reaction to occur? Go ahead and measure out the solutions you'll need for the next step. Do you need to record a mass too? Maybe go ahead, weigh out that watch glass and filter paper. Is there some glassware that you can go ahead and clean so you're ready to leave the lab on time? Identify these steps so you can use your time efficiently and successfully. And when in doubt, before lab, speak with your TA in the General Chemistry Learning Center or ask the lab supervisor if you have questions about the procedure you're performing in lab.